Hi everyone, this is Rosario Borgesi. Welcome back to the channel. In this video, we will explore Layer 2. We will understand why Layer 2 have been created to enhance the Layer 1 scalability. We will also discuss the difference between Layer 1 and Layer 2, and we will also explore rollups, which are a particular types of Layer 2, and the difference between zero knowledge rollups and optimistic rollups. And at last, we will understand the concept of bridging tokens between the different layers. So let's get started. This is a Medium article that I have created to help us throughout the video. Let's start by explaining the difference between layer 1 and layer 2 blockchains. So a layer 1 blockchain, it is the main blockchain that does not rely on external system. For example, Ethereum or Bitcoin or for example also Solana. A layer 2 blockchain, in contrast, it is another blockchain, a parallel blockchain, we could say, that it's built on top of the layer 1. So, for example, here we have 3 examples of layer 2 blockchains, which are Optimism, Arbitrum, and also Starknet, which are built on top of layer 1, which is Ethereum in this case, to improve scalability and efficiency. Basically, what they do is that they process the transaction off-chain and periodically post the record summaries on the underlying L1 blockchain, in this case Ethereum. And this is done, of course, to enhance the transaction speed and to reduce the costs. Let's talk about now the blockchain trilemma. As you can see here, this trilemma was proposed by Vitalik Buterin. There are three features, three attributes of a blockchain, which are scalability, security, and decentralization. And this trilemma asserts that we could only optimize two attributes of the blockchain, and we could not optimize all these three properties. For example, Bitcoin and Ethereum prioritized security and decentralization over scalability. And this is the main reason why layer 2s have been created to address the third problem. So this basically means that if I create a blockchain, a new blockchain, I can only improve at the same time security and decentralization, but I cannot have, for example, scalability, or for example, I can address the security and the scalability, but I cannot improve the decentralization. So as we said before, the reason why the layer 2 have been created is to address the scalability challenge, because as more people use the Ethereum blockchain, the transaction become more expensive and also slower. This, of course, creates a barrier for the mass adoption of the blockchain. And to give some numbers, we can say that, for example, the Ethereum mainnet processes only 13 transactions per second, while Visa handles around 1700 transactions per second. So we can understand from this number how much less transaction the Ethereum mainnet can handle. So Another solution could be simply to increase the number of transactions per block on Ethereum, but this is not feasible because this could raise the cost of running nodes, and in this case we would discourage decentralization, and also larger blocks would destabilize the consensus, and it is not a good a, a good path to follow. Layer 2 blockchains are parallel blockchain to the mainnet. And so in this, by using a parallel blockchain, we are offloading the transaction from the main chain to from the layer 1 to the layer 2, and in this way we can address the scalability issue. This is the main idea behind the layer 2, and this would boost transaction throughput, would lower costs, and of course enhance the overall user experience, and also we would keep the security and decentralization of the underlying layer 1. There are various types, various technologies and frameworks that have been developed to address as layer 2s, like rollups, state channels, and plasma, but we will focus in this video on rollups because these are the most prominent solutions. So, as we said, rollups enhance layer 1 scalability by offloading most of the heavy computation to a secondary layer, so a parallel blockchain. As you can see here, you have this is the main the layer 1, the main blockchain, and the layer 2 blockchain, which uploads, which processes the transaction independently from the layer 1, and then uploads the transaction to as a batch to the layer 1. So in this way we can the layer 1, it is relieved from a lot of load that must process it, because this load is processed in another chain, so we can reduce the pressure on layer 1 and have the scalability. So, as we said earlier, instead of processing transaction one by one on layer 1, the rollups handle them on layer 2, which is more cost effective. Then they group multiple transactions into a single compressed summary and submit it to layer 1 for verification. This, of course, brings several benefits like lower transaction costs, faster transaction processing, greater functionality, and also, of course, we inherit the security from the layer 1, because since the rollup publish the transaction layer 1, we are still making use of the layer 1 mainnet, or layer 1 security on mainnet. So there are two main types of rollups, which are optimistic rollups and validity rollups. The optimistic rollups assume that all transactions are valid by default, and to prevent fraud, they include a dispute resolution system, which means that basically anyone can challenge a transaction, can prove that a transaction, that there is a fraud in a transaction, but within a period of a week. So if a fraudulent transaction is detected, a fraud proof is submitted to prove the error. Instead, validity rollups rely on disputes and validity rollups require operators to submit a cryptographic proof verifying the correctness of every transaction in a batch before it is finalized on layer 1. So while here we are basically saying, okay, I trust you and your transaction. If someone finds a transaction that is fraudulent, they must give me the proof that this transaction is fraudulent. In this case, in the case of validity rollups, it is the rollups itself that provides a proof of the correctness of every transaction in the batch before it is uploaded onto the layer 1. So the key difference is that optimistic rollups depend on human intervention to catch fraud, while validity rollups rely on mathematical proof. And this makes, of course, the process more secure. And also, validity rollups do not require a challenge period, um, whereas the optimistic rollups may take up to a week to finalize this batch of transaction. So let's make a deep dive into validity rollups. So the validity rollups are also called as known as zero knowledge rollups, and the basic principle it is that they aggregate multiple transactions into batches that are of course processed off chain, and this batch is then posted to the blockchain instead, of course, of submitting each transaction. They submit a batch, and this, of course, offloads a lot of transaction from the mainnet. And they also provide validity proof of this transaction. So the state of the zero knowledge rollup is managed by a smart contract on the Ethereum network. To update this state, the zero knowledge rollup nodes must submit a validity proof for validation. This is a cryptographic proof that guarantees that the proposed state change corresponds to the execution of the batch of transaction. So the zero knowledge rollup only need to submit the validity proof to finalize the transaction on the layer 1 Ethereum, unlike optimistic rollups, which require posting all transaction data on chain. So the transfer from zero knowledge rollup to Ethereum occur instantly because exit transactions are processed once the validity proof is verified by the zero knowledge smart contract rollup, the smart contract of the zero knowledge rollup. In contrast, the withdrawals from the optimistic rollups are subject to delays, and because, as we said earlier, we must allow for the time for to challenge the fraud. Um, so this validity proof that we were talking earlier is a cryptographic guarantee that batch transactions have been processed correctly. These proofs are called zero knowledge proof because they verify the correctness of a statement without revealing the statement itself. So, zero knowledge rollups use validity proof to ensure an accurate off-chain state transitions without the need to re-execute transaction on Ethereum. Sorry. This is an important point for us developers. So, unlike optimistic rollups, zero knowledge rollups are not inherently compatible with the Ethereum virtual machine. This means that the smart contract that we have written for Ethereum cannot be in Solidity cannot be deployed on a zero knowledge rollups because they have a different virtual machine. And this means that, for example, like it happens in Starknet, they have their own programming language, for example, Cairo for Starknet, and so we must write the smart contract in another programming language most of the times because they are not compatible, but there are have there are there is a significant effort to move towards a compatibility between the a virtual machine of Ethereum layer 1 and the virtual machine of the zero knowledge rollups. The difference of this 0K virtual machine is that they have to generate a zero knowledge proof to ensure the correctness of each step in the program execution. This is the main difference between the zero knowledge EVM and the Ethereum EVM. There are various examples of zero knowledge rollups. The most important ones are Starknet, as we said here. It is a rollup with a native account abstraction and its own programming language, which is Cairo, that optimizes for leveraging validity proof. Then there is also Zero Knowledge Sync, which is another leading validity rollup with a native account abstraction that runs on the Ethereum virtual machine. Then we have Scroll. We have also Polygon Zero Knowledge EVM, and we have also Linea. For example, this is provided by Polygon, the Polygon Zero Knowledge EVM, and we have also Linea, which is powered by Consensus, so which is the company behind MetaMask. So these are the most famous. So let's jump into Optimistic Rollups. Similarly to the zero knowledge rollup, because the principle behind the scene it is the same. Optimistic rollup enhance Ethereum scalability by shifting computation and state storage off chain while still posting transaction data to the Ethereum mainnet. So the principle it is the same, but what changes is that they as we said earlier, they trust that the majority of the transaction are valid. If we want to a transaction that we want to prove that is fraudulent, we must prove it with the fraud proof mechanism. This, of course, allow to reach, of course, 10 to 100x scalability improvement, because, of course, instead of executing each transaction on the Ethereum rollup, we bundle this transaction into large batches, and of course we don't have to we are not executing the mathematical proof that have been that are instead executed in the case of zero knowledge rollups. These rollups post transaction data as cold data or in blobs, and this makes the execution significantly cheaper. So the term optimistic refers to the assumption that off-chain transactions are valid by default, unlike zero-knowledge rollups, which provide cryptographic proofs for each batch. Instead of upfront validation, optimistic rollups use a fraud proof mechanism. So once the batch is submitted to Ethereum, a challenge period begins, allowing anyone to dispute incorrect transaction by submitting a fraud proof. So if a fraud proof is successful, the incorrect transaction is re-executed and the rollup state is updated. Then the sequencer responsible for invalid transaction faces penalties, and if no challenges arise within the given period, the batch is considered valid and finalized on Ethereum. Um, Optimistic Rollup also are governed by smart contracts deployed on Ethereum mainnet because, of course, like in the zero knowledge blockchain rollups, we always need a smart contract in the layer one that allows this batch of transaction to be um, submitted to the layer one. So to communicate from the layer two to the layer one, we need always a smart contract that allow to deploy this transaction, this batch of transaction. So while transactions are processed off-chain, they are periodically bundled and submitted to an on-chain roll-up contract. This is, of course, this record is this transaction history. Then, when it is finalized, becomes immutable, and this is known as the optimistic roll-up chain. So for developers, which we are, the key benefit in this case of optimistic rollup is that there is a seamless compatibility or even full equivalence between the Ethereum virtual machine and the virtual machine of the rollups. So this means that the smart contract that we have developed for example, Ethereum layer 1 in Solidity, we could deploy this same smart contract on a layer 2. And this, of course, it is important because the smart contract on layer 1 have been been audited, and so they are much more secure than some smart contracts that have been less tested on a layer 2. So we also inherit the security from the code standpoint, from the code standpoint. So the most important, the most prominent rollups in the ecosystem in this moment are Arbitrum, which is the largest optimistic rollup in terms of TVL. Then we have Optimism, which is the second most important, and then we have also Base, which is provided by Coinbase. Now, there is an important thing to understand, which is the topic of bridging tokens. So when we have some tokens, for example, Ether on a layer 1, which is, for example, Ethereum, and we want, for example, to move these tokens, this Ether, sorry, on a layer 2 like Optimism or Arbitrum or whatever, we should make use of a bridge. A bridge basically is a smart contract that locks the token in one chain and then means new token, creates new token in the chain where we want uh, our token to be. And so this smart contract allow us to move, of course, the tokens, not only Ether, but also ERC20 tokens from one chain to another. And of course, this has a cost. We could also do the other way around, so from a layer 2 to a layer 1. But this, of course, has high costs. But it is important to know that if we have some tokens on the layer 1 and we want to move these tokens to a layer 2, we must use a bridge. So the tokens that we have in each chain, so this to go back to the point that we were stating before, that layer 1 and layer 2 are two separate blockchains, each one with its own tokens. So if we have a tokens on layer 1, these tokens are not available on layer 2 unless we bridge them. So we have reached the end of the video. If you have any questions, please drop a comment below. Thank you for watching and see you in the next video.